So should I start now that you're here? All right, well, thanks. Hopefully this will be a lunchtime that you'll take some things away from this. And if you can't hear me in the back, please raise your hand or something like that. So I appreciate it. So I've been wanting to do something like this for a period of time, and the reason being is a couple of difference. One is to kind of highlight an observational challenge that we have, and also a forecasting challenge that we have, and also sort of give you an idea of some of the capabilities that exist in this modern era. We're actually going to look at ships and their tracks because we're going to look at the impacts. So kind of working the problem. If you can't observe it, if you can't predict it, at least you can figure out that there's an impact and get an idea as to what the extent of the impact is to vessels transiting the Gulf Stream. So, and this problem is not necessarily isolated to the Gulf Stream. It actually is where you have strong currents interacting with waves and winds. It just happens on many, many different scales, and I think that's true for the stream also. So I don't, like all of us, I don't work in a bubble. I'm the one doing the presenting, but many of these slides and content of the slides basically have been put together by a variety of different people. Both Fran and Jason from the Ocean Prediction Center, and then also Olivia Keith, who at the University of Miami, who was a student, one of the NCEP La Penta interns from last summer, and Liv really rolled up their sleeves and dove into the data and was able to extract a lot of information out of it. So let's go ahead and start. So there's a bunch of different things that happen. I'll reiterate this afterwards. I'm going to show you visibly what some of these are. Okay, one of them is the possibility of wind blowing against current, basically having an impact on the waves and actually decreasing sort of the distance between waves and basically increasing the encounter time for ships. Also, there's the potential for breaking wave conditions in this. We don't quite know how much of what we're seeing for impacts is due to that. Another, which is sort of a greater, we basically have an ocean front that's very, very intense at times of the year, especially in the springtime, offshore. And we actually get to see using, and I'll show you with the stability is the next thing, but basically there are some thoughts that this ocean front presents itself in the form of an atmospheric front. And in fact, there's a nice paper about Sandy and the role of a vorticity reservoir, basically, along the Gulf Stream that Sandy was able to tap into. And in reading Tom Galarno's paper with Mel Shapiro, the role of the Gulf Stream in the track of Sandy, in other words, the development or the intensification or re-intensification of Sandy was not of tropical origin. It was not barotropic. It was baroclinic. And the Gulf Stream front, atmospheric front, was basically the contributing to that the vorticity reservoir. Okay. It's also, when I did my thesis work on the Gale experiment, is a focus for thunderstorm activity. And I tracked back then in the 80s, 1986, basically, you could track thunderstorm activity starting, forming on the Gulf Stream, convergence, there's like a sea breeze circulation, and then actually moving off, and then another set of thunderstorms, a line form in the shape. You could actually trace in the thunderstorms the shape of the Gulf Stream. Okay. Another issue that we know from our scatterometer work is changing and mixing due to static stability, changing across the Gulf Stream. Over the warmer water, you have enhanced mixing, and then over cooler water, especially when you have flow going from the warm water to the cooler water, you actually see a significant reduction in the surface impact of the wind. Basically, the scatterometers do not measure the wind, they actually measure the impact of the wind. So you're looking at really wind stress. There's a significant reduction in the wind stress in certain flow regimes when you go from warm water to cooler water. Okay, and the last one is basically, which I think is the most challenging, is there's an interface. You have a current maximum, you have thermal gradients, but you also, with the current maximum, you have shear on both sides of the Gulf Stream. Okay, that's a boundary. So wave energy actually refracts and can be focused into the Gulf Stream across that boundary. Okay, I'm watching Enrique. Looks doing okay, right, with that? Yeah, okay, whatever. Anyway, I'll show you an example of that. Okay, I think, in my view, this is the most challenging because you have to get the gradients correct, and they're on small scale. All right, that's my simple view of that. Too bad if it's not right. Okay, so this is the rule of thumbs. This is basically, it's a derivative of what the Navy's thinking about after having ship incidents in the Gulf Stream. And the idea was opposing flow to the Gulf Stream with the flow to the northeast as it turns to the east. In this area where you'll have higher winds and seas. Okay, so that's one. And this is one of our own analyses from years ago with 11 to 12 feet. And this was done by Lee Chesno, and he basically said we need to highlight the Gulf Stream better. You'll see as we go along. The other is enhanced mixing downwind of the Gulf Stream and along the boundary with downwind gustiness and enhanced waves. Oh, I wish it were that simple. And I think that's what I'm going to try and have you take away from this. Okay. This is Plum Gut. So this is between Orient Point, the North Fork of Long Island, and the Plum Island. And the tide runs very, very strong. The current is relatively strong in this area. I was actually on the ferry when I took this picture 15 years ago or so. Buoy for a reference. The flow is actually, it's flood, so it's actually, even though it doesn't look like it with the buoy, it actually is coming this way, and the wind is blowing in this direction. The flow actually flows west-northwest, and the wind was actually from the west-northwest. So, oceanographic and atmospheric conventions. Okay, so you see that patch of white water or rough water. Okay, this is the nautical chart for the area. That's this buoy. Okay, Midway Shoal. We're up in here somewhere, looking in that direction. You can't see Plum Island. And in here, that's where you're looking, where there's a sharp gradient of bathymetry. So you're going from relatively shallow water to deeper water to very, very deep water. So there's a shear line in here of current, and you're seeing basically a combination of wind and current and wave interaction. Whitewater in that area. Okay. This is a picture from the early 80s. And this is a tanker, an old-style tanker. It's actually Gulf Oil had tankers back up until the early 90s, and this is a Gulf Oil tanker. A colleague of mine at Maine Maritime, Andy Chase, did not take this picture, but he was standing next to the guy that did. Okay. All day, this is east of Charleston in the Gulf Stream. They're riding the stream for the current boost. First thing I want you to look at, don't look at the ship or the wave, but I want you to look in here and get an idea. Is there a lot of wind? Is there much wind in that case? 15, maybe 20 knots. Okay. That's about a 60-foot wave, by the way. Okay. So there's a storm way up to the northeast with northeasterly, producing a northeasterly swell. During the morning before this happened, they'd seen breaking waves off in the distance. And it is hard when it's close to the horizon to sort of judge distances when you see something like that. They actually were talking about whales breaching. Okay? And then they encountered this. Okay. So this is a trapped wave, swell from way off in the distance. You can consider this to be a rogue wave. So that wave went across the ship at about that height. This is a loaded tanker. She didn't lift in the wave because the face of it was so sharp. So the wave just basically broke down the ship. They were on the bridge wing. The bridge wing flooded. They managed to hang on and not go over the side. The wheelhouse flooded. The firefighting station right here, that orange thing there, was torn for its moorings. This mast was bent backwards. 15 to 20 knots of wind. So you wonder why freak waves, rogue waves, why they have those names, something like this happens. That's in the Gulf Stream, east of Charleston. We'll look at another example, east of Charleston. Not as dramatic as this, but it's pretty dramatic.
Were there no more pictures?
Of that?
Yeah.
No. And by the way, this wave, as you can see, look at the face of the wave. You can see it kind of looks like it's sort of rolling backwards, but actually it's about to break on them.
Can you point out the portal? Can you see the portal on the side for scale?
Portal.
Out on the bow.
Up forward. I'm looking at the.
Right there.
Is it port? I can't see the port.
It's the door.
These are doors, okay? So, yeah, as they like to say, they make the doors on ships for a reason this way, so you can bang your shins and bang your head. But these are dogged down so that they're the equivalent of basically is the steel that surrounds them. Yeah, so that door is about that high just for scale. So I know I don't have to duck through going through that. I just have to lift my legs going through. So it's about this high, just for scale. Yeah. All right, so for sake of time, I want you to focus in here. All right, so this is goes 16, or goes east. This is actually reversing the color scheme. So blacker clouds, the white are the warmer temperature of the underlying ocean. You can see the gradient, it's how sharp it is in here. I'm looping this as fast as AWIPS can go. And what I'm without some manipulation that you can do in the background. What I want you to see, I want you to watch the ocean right in there. So the ocean moves on the mesoscale, very short time scales. And those features, sharp gradients like this, of both current and thermal gradient, you can watch there are edge waves in here. Some are dampening, some are amplifying. And then you can see this curl, so this Gulf Stream water that has come off, basically, and is flowing back down to the southwest, and you can see a circulation right in there. And there are others you can see up here. This, in my mind, we're going to, as we grow, getting used to GOES 16, the GOES R series, this is something we're going to use more of. It's phenomenal as to what you can see. This is the CONUS scale, so this is 5 minutes. And you can see how rapidly the underlying ocean is changing. It's not static. So when we look at something like this, and that's AMSR 2 of the same day and the same time, it gives you an idea of what the microwave that can see through the clouds at about 25 kilometer resolution, or maybe even coarser than that, as compared to the fine, fine structure that we see. If you're in a sailboat or you're transiting and you're watching the sea surface temperature, you're seeing all of these features. And like I said, they evolve very, very quickly. So that's a challenge, not only observation-wise, but also current. And you can look up in here and just watch these features along the shelf break front, which is pretty ragged, but you can kind of see where some of the features, even those are moving very quickly. You can actually, with this, you can see the tidal nodes. There's an element of that is up in there off of Georges Bank as a tidal node. Okay, so stratification. This is an oldie, but it still works today. And I like this for one simple reason, is look at the gradient of the isobars here. One would think if gradient were the only thing that was producing surface wind, then one would think you'd have a relatively uniform wind field of a south-southwesterly from, say, off of, way east of Savannah or Jacksonville, all the way up to the frontal boundary just to the north of Cape Sable, Nova Scotia. The purple in here is where you'll see that there are actually wind features. So this is in the Quickscat day. Okay, remember there was an eddy up here. Here's an area of 30 knots of wind. The color scale is up in the upper right. Okay, so right in here is an enhanced area. There are weaker surface winds, or the reflection of the wind at the surface is much weaker than it is here. And that aligns, I'll go back in a second, that aligns fairly well with the, well, you'll see in the next slide. Okay, then you see this boundary. There's actually gale force winds here, 35 knots of wind. You've got 15 to 20, 15 knots in here. Remember the pressure gradient? Yeah. In my day, we actually started by measuring gradient. Yeah, we weren't very good. We were doing what we could do at the time. And you can see that extend all the way up. All that gradient is pretty uniform all through there, and you can sort of see how the ocean is actually impacting the stratification. So and this is the challenge back in the day, as to how to get an analysis that actually matches up with the time where it's cloud-free. Lo and behold, there is an eddy up here, a warm eddy. Here's the main body of the stream, and they match fairly well. This is, I can do it here, actually. If I go back. So you can see how basically the ocean, through mixing, is actually impacting the wind field, or the surface wind field. And I had the pleasure about 10, 12 years ago to visit with racers that were in the Volvo race, and they had raced from somewhere south to Boston. And they were coming into Boston up here. And they were telling us that they had 100-foot masts, and they were doing 25 knots. The water was glass. There were no ripples because there was no wind on the surface. Everything was aloft up there. They're blasting. That's fun. You're going 25 knots in flat water. I mean, that's like a gift. But yeah, I mean, that is kind of the way it manifests itself. All right, let's keep trucking. Okay, so I kind of went through the trapped. Paul Chang, if you know Paul Chang from Nessus Star, Ocean Winds team, basically took this years ago from the P3, flying out of PAX. And this is the stream here in a northeasterly flow with the current going in that direction, and here is north of the stream. Roughness, kind of on a different scale, but similar to what we saw with in Plum Gut, and then much calmer manifestation to the north of the Gulf Stream. And this is just another example, a more recent example, but here you see these patches, and we're used to seeing this of wind, and when we look at the underlying surface, basically, this is where the stream is, typically. You can actually see the wind field in the right flow regime, typically a southerly, where it actually maps out the underlying ocean due to the stratification. Okay, I forget what's next. All right, I told you we'd look at ships. Okay, this is last week. We had a big northeasterly fetch offshore. There was a storm down here, actually ended up being two different storms. One moved out relatively quickly, and then the parent actually sort of stayed around for a period of time with storm conditions. This is a big ship. So this is the Overseas Orient Container Line's Bangkok, 13,280 TEU. So divide that in half, and that's the cargo capacity for the number of 40-foot containers it can carry. So that ship can carry 6,500, 6,600 trailer trucks. Okay, its carrying capacity is 144,000 deadweight. That's metric tons. So, and come over here. This is the information in this message, the AIS message. This ship is 366 meters in length. So it's 1,200 feet long. So one would think that's a kind of a pretty stable platform, safe ride to go across an ocean. Left Charleston. She's going to the Suez and points east from there. These are the plots of the position of the ship via the automatic identification system. She comes out of Charleston doing about 13 knots. This ship typically runs at 18 knots. Okay, a little bit of a crab angle because of the wind. That's my assumption. Okay, and then as it approaches this little turn in the Gulf Stream, 11.6 knots, enters into the stream. She's doing 5.1 knots. Slows down to about 4.6, gets midstream and starts to accelerate. Finally, he's doing 14 knots out here. Now, this overall, in conditions of northeasterly flow, one might think that it might be 40, 50 knots of wind. It's 35 knots of wind. That's our minimal warning criteria. So, waves, maybe one might think, as to why they're having to slow down going across the stream. Again, it's a 1,200-foot ship. They're going to make them bigger. They're in the process of making them bigger. That 13,000 TEU, this is a 7-year-old ship, is becoming something like 22,000 TEU. So carrying about 11,000 containers, 40-foot trailer trucks. They're massive. Those ships will be about 1,400 feet long. Okay, so this is the ASCATs, and yellow is gale force, same wind scale. So 30 knots, and then right in here, this is where the ship was when it was most slow, is into the Gulf Stream, and 35 knots as inferred from measuring the ocean roughness. And here you can see there's some storm. Actually, there's a little bit of violent storm down in here. So that's where the one low was, and then there was the other one that peeled off from it. But anyway, so 35 knots of wind, maybe 40, but no more than that. This is from altimeters, and if I remember right, I can't tell if that's orange. I think it's not yellow. I think it's the orange. So that would be Sentinel 3B, and then this, if I remember right, is Cryosat. So wave heights are up here. They're in feet, and 21 feet. Remember, the ship was right in here. I thought I had the circle on there, but the ship was right in here, kind of a little bit lagging behind in the past at 1533. The ship was here about 12Z. But there is a gradient as you go into the stream of up into the low 20s, and you're going from 13, 14, 15 up to 18, 19, right through that transition right there. So it didn't quite capture the right location. And same thing here, you've got in the low 20s right in there in the Gulf Stream. So a little bit of evidence, but it's very challenging to match up ship positions with the passes from the altimeters or the scatterometers just because of the frequency. And these are the traditional buoys. So 9 feet, 30 knots, gives you an idea as to what was going on there. And then this anemometer is out. And then this ship reporting 15 feet, 12 feet off of St. Augustine, NOAA buoy. This is wave watch. This is we still create a subset, but this is the West and North Atlantic tile, I guess you'd want to call it, or subset of wave watch. But this is where the vessel is. So 21 feet here. I just showed you the altimeters. There's a 12-hour forecast, and here that's the 18-foot contour. It's suggesting in there that there's 18 feet, but there's no reflection because it's not. We do not have that capability at this point of any kind of wind wave current interaction at this point in wave watch. So that's a prediction challenge. Okay, and then this is wave period, dominant wave period in our world, and the direction. So you basically see everything is aligned. Wind wave and swell, everything is aligned from the northeast with the persistent northeasterly flow and the high over the U.S. And this one I'm going to apologize with. It's only because I had it, but this is NCOM, only because I did this too late and the RTOFs had already gone. I didn't have RTOFs for this time in our thing. But you get to see some of the challenge. There's a hint of this with what they call the Charleston bump, where you actually do get a relatively persistent, but not all the time, relatively persistent sort of bend in the Gulf Stream and a little bit of acceleration northward. And then you can see here there's a bit of a displacement in here as opposed to, this is the Navy's north wall, and then the south wall of the stream is a dashed line, which you can barely see in there. But it gives you an idea of where the flow is, and where we saw the ship slow down was right in here. And that slowdown, that significant slowdown, if that is not due to adverse, the ship opposing the current, that it's much, much larger than that. Okay. Another example, this is the windstorm that we had in March of 18 when it moved offshore. It was a snowstorm, windstorm, a variety of different things. I think it's the day after the government was shut down, but the storm had moved offshore. And here, although it's clouded over and goes, but here is basically where the stream is. And we've got seas of 30 feet, a little bit higher than 30 feet on either side of the stream. And right in the core of the stream is up over 40 feet. And this is in a northerly flow. Current is flowing like this, and a northerly flow. And we've got relatively large waves. And there's a really big northeasterly fetch up to the north as the storm evolved. So whether this is wind versus current or a combination of that, and the fact that you have perhaps waves that are abducted in the stream with swell, have to be diagnosed. This is a summer example. So there's a hurricane force low to the southeast of Nova Scotia. And I'm assuming this is a recurving tropical cyclone since it's August 31st of 17. I should remember this because I was on forecast desk. That's actually my analysis there. And here, it's really easy when you have a color scheme and it stands out when you look at the altimeter data. This is Altica. And background field is 7 to 8 feet. And you've got almost double, actually more than double that, almost 16 feet in the core of the stream, right in this area. But the wind here is westerly or northwesterly, 15, maybe 20 knots, not much more than that. And meanwhile, you have this storm pass to the north, to the east, and either it's swell as the storm was moving, or swell, we really don't know, except for the fact you're seeing it manifested over the doubling of the significant wave height in the stream. And just this is GR tops with the current maximum right through where the maximum seas were. Okay. Whoops. And last one, this is February, this is 4 years ago. This is February 8th, the morning of the day after Super Bowl Sunday, and where there had been issues. A cruise ship was caught in the storm as it was rapidly intensifying down here, and actually observed 131 knots, a 5-minute average wind, and had 100 knots over a 40-minute period. So in this is a max of 40 feet, 34 feet, and then this could be right on the northern edge of the stream. One may think that actually the stream is not in that location based on the Navy analysis. This is on a Monday. The last analysis is on a Friday. And one of the reasons why I want to show you how dynamic the ocean is. Okay. And, all right, this one I want to this is one I want you to remember. Okay. So, along this line, this is a track from, if I remember right, Jason 3. Yeah, it is Jason 3 because it was right after launch. So it was early April. And, a sort of triple low center, long northeasterly fetch, again, seems to be a theme. And there's a track of altimeter from here to here. And this is an ocean model that's underneath showing a representation of possibly what the current is. Okay, there are 3 graphs here. Actually, there's 4, but I'll talk about 3. Okay, so there's the Jason 3 processed by 2 different Meade and Newton-Raphson here. Okay, this is a model. Fabrice Arguin had given me this. This is, I assume it's a wave watch. It may not be. But a wave model, and this is without any representation, without coupling of any representation of the current. This is with current, so this is with coupling. So there's a little bit of an enhancement in the waves up to about 4.5 to maybe a little bit higher than that here. This is Jason. Okay, up to almost 6.5 meters right in there, again, in the stream. So it's one of the reasons, Eric, why I wanted you to kind of see this. You've probably seen this, but something we've talked about is we don't see, just because of the scale that we see, we don't get to see this level of detail, and it would be interesting to start to compile things. Okay, here's another example. This is a tanker that has departed Newfoundland and is sailing south and is right about underneath the T in storm. Right there. Okay, so you can see the track of the ship turns as the wind is increasing, and then gets to a point where they enter the stream. And this ship basically is what we call hove to, is headed into the seas, headed into the current, and headed into the wind, and is moving a grand total of 2.3 knots. Is pointing 287 degrees and is moving 241 degrees. So basically it's just sliding ever so slowly. So impacted vessel losing time, but is doing that not because of time, but because of what the conditions are doing to the vessel. They're responding to the conditions to keep their vessel safe. It's an impact. Okay, and yeah, there are big seas, 37 feet, something like that. Okay, this is a more recent example. This is the 28th of November. This is Thanksgiving morning. This is a westbound container ship, and actually is just running along south of the Gulf Stream with a cold front approaching, and then basically having a frontal passage as they were entering into the Gulf Stream. That's actually this vessel's observation of 35 knots of wind somewhere over in here. This is more like around 11Z. And I like this example. One is he's had to slow down 18 knots down to 12 knots. We don't get to see the detail of what the vessel went through coming into the stream. So the next best thing is to ask the captain. That's the ship. That's the Maersk Ohio, bound, I think, for Norfolk. So, Captain Kavanaugh. So we encountered the stream around 11Z. It was a little bit after that based on the positions, okay, and where. And swells were confused and massive. Okay, once we got through the south wall, so remember the rules of thumb that we see that don't mention the south wall? Yeah, so he's basically experienced similar conditions that one would have expected on the north wall and the south wall. Sea became more predictive and uniform once they got into the main body of the stream. Winds were a steady Beaufort 10 to 12. Okay, remember there's no 13. And at times exceeding 100 knots, veering from south-southwest to north. He went through a frontal passage. So not only do we not see basically the confused and massive seas, we really don't have an observing capability except for perhaps the ship of seeing winds of that strength. I went back and looked at the scatterometers, and they were up around 45 to 50 knots, but no more than that. So what they're experiencing on the scale that they're at, just like all of us, is quite different than what typically we see in observations or predictions. I see Brian's nodding his head. So this past summer, we worked with a student, and we actually started this effort a year ago, and just looking at ship tracks going through the Gulf Stream and saving them with the hope that we could actually make some sense out of impacts. And there's bias in this. It's my bias, basically, is I'm the one that picked about 200 different passages across the Gulf Stream, and because of the potential for seeing impacts. So let me go ahead and Liv Keith from University of Miami did this and really did a very good job, along with Jason Kreckler, who had worked doing some of the plotting, and then also Fran, who did an enormous amount of work trying to basically do some analytics and come up with perhaps some interesting points as the conditions and all. So this is color-coded by the speed of the vessel. So we did 12 knots all the way down, and we actually we binned the vessels. We only did 26 of them as opposed to the 83 starting with, as opposed to the 200, which was the bigger just because of time. So the yellow to more of an amber, and then really slow is basically 2 knots or less. And you can see for some of these are all 26 of the tracks through the Gulf Stream. And you see some really interesting things. That, for instance, when they're opposing, you'll actually see that the ship's actually, like right there, slow down. And that may actually be the impact of the current. Okay.
Question, though.
Yes.
So are these, the speed itself is a constant? Say there is no Gulf Stream, there's no wind whatsoever, it's supposed to move in a constant
That's
speed?
typically the way they operate.
That's what it is.
Yes.
And then those speed down, it has to do with the water environment.
That's the assumption, mm-hmm. And not going any more, where it's a combination of wind mm-hmm. and wave action. Yes, yeah, or wind direction and wave action. Depends on the type of ship. This is just 2 examples, and here you can see impact. This is actually a bulk carrier, a relatively small bulk carrier, relatively small meaning 229 meters, as opposed to 366 I just showed you. And this actually is a product tanker, or we used to call them drugstore ships in my merchant marine days, but basically a chemical or oil product tanker. Yeah. Working on drugstore, it meant that it carried all kinds of different things that could not contaminate each other, like lubricating oils. So in other words, it was a nightmare to work on, because, you hear stories of, I remember a classmate, years later told me about, they put paraffin into a non-heated tank,
How do you get that out? With a jackhammer. It's a way of getting fired. It keeps you moving around. Or you contaminate things. I mean, this kind of ship you didn't really want to work on because it was a lot of work, and especially in port when it came to discharge. Anyway, so you can see this westbound ship going into New York, and you can see the stream here, slowing down there, a little bit of a slowdown here, and another one here as it's progressing westward. And one of the revelations we found with this study is the fact that the impacts, as far out as the Navy basically tracks the Gulf Stream, we see impacts. And in this time period, you actually see more impacts out here than we do along the coast. But that may just be the weather during that time period. And his one here that's in the stream actually got down to less than 2 knots as it was traveling westbound and is back up over 12.
Joe, so
Yes,
what
sir.
is the time in that picture? What does it understand?
So that could be several days, depending on the speed of the ship. That might be like 2.5 days. We could actually go back and we're using a web application that was developed by the Department of Transportation for displaying this data in real time. And does anybody remember what I know I grabbed different times, but I could grab tracks as long as 6 days. So that would be the starting
I
point.
don't know how long they were, and I think we actually, I don't know if Liz did it for this, but for some of the analytics, they cut down the time frame to just when the impacts were. We would just look at that.
Right.
Other times we would look at just every single data point you had. But it has a timestamp, but every single one of those points has a date, time, and speed, and that on.
Yeah, I mean, some of those reports are like by the minute.
Right. And they're actually more frequent than that if you're closer into... These are acquired by polar orbiting satellites, so communication satellites. So Orbcomm, Spire, basically have satellite systems that are actually downloading this. This is a VHF broadcast, which, is line of sight. So if you're above it, you can actually hear the broadcast. This does struggle depending on the frequency drops when there aren't the satellites, obviously. The other times that it struggles is when there's many different signals. So for instance, off of Asia, where the traffic density is phenomenal, that the satellite acquisition doesn't work very well because it's just saturated. Actually, the land actually has problems too because the traffic density is so high.
Andre.
Yeah, Joe, so if you integrate that in time, what's the economic impact? How much delay would a ship like that see because of all this action?
That's our next. This was just a tease. We wanted to make sure there were impacts first, but we could actually start to calculate time lost. Make an assumption, optimum speed, and then go ahead and find out that these ships are losing 2 days, coming across the Atlantic, or 3 days coming across the Atlantic, and then work that out over time.
And just even just the delay of just a few hours could make a big difference in a large port when all the ships have to queue in to get the stevedores and the cranes to get the stuff off with the trucks waiting. It could back up many other things. So the cost in just a few hours of delay could be really a lot.
Yeah. Or you lose your berth, and now you go back to the back in line. Yeah. Walter.
So Joe, in one of your earlier examples of data like this, you showed that the vessel heading was quite different from the course made good.
Yes.
Because they had essentially turned their bow into
Yes.
seas or the weather or whatever. So in this data set, in addition to, you're just plotting speed made good here, I guess, but you also have the heading information. So
Yeah, you can. It's a little hard to see. This one, it gets a little cloudy in here, but there actually are directional changes in here. In this one right in here, they're significant. This ship is basically heading that way, but for a time period, it's headed more west to west-northwest, then actually turned down to the southwest.
The little arrowhead, the symbol, and the arrowhead changes direction based on the heading, not the course over ground, but where they intended to go.
Okay, so from where I'm sitting, I can't see that.
Yeah,
You can clearly tell when the seas or the weather they're encountering are absolutely dominating everything they're trying to do next.
Yes.
From the data set.
Yep. Yeah.
You also presumably have a first guess at the current speed. So if it were not winds and waves, we could calculate what in other words, the difference between the course and speed being good and the course and speed and the RPMs on the screws and the heading, the difference in those two things you would expect from simply the running of the water.
Yes.
You could estimate that.
You could estimate it as long as, yeah.
Is caused by the seas that are encountered.
Yeah. This is the breakdown of 26 vessels. So we saw a lot of smaller bulk carriers, meaning bulk cargo, not containers. Might be iron ore, could be grain. My favorite in the Pacific is timber ships, where we saw one coming back east today, empty, and was not in a good place again. This is a crude oil tanker, and we don't know, and this is one of the findings, is we don't know, whether these ships are in ballast. We used to say light, but basically in ballast, meaning empty, or whether they're loaded. One assumes that a tanker like this, where it's most impacted, would be in ballast when it's running empty. Chemical product tankers, sort of a general cargo, which is sort of similar, but they're broken out differently the way that the AIS does it. And then we had one vehicle carrier that actually looked like it was sort of sailing in the Gulf Stream. And this was more off of Charleston area. And that may have been, and we can't, the reason why the ship is doing that, maybe because it's waiting for berth, and it's the easiest place for it to wait and just sort of, but we have no way of knowing that. And a heavy lift ship, here we're actually, this is how they transport container cranes across an ocean. My mother would say something like, God love them. Okay, so here's a more detailed example. This will help. One more. There, we'll do this. Okay, so this, we're assuming, is an in-ballast. This is a fairly large ship, 250-meter crude oil tanker. And coming south, assuming in ballast, actually turns to the west with speed, and then actually slows down as it turns south, and then basically almost sort of like sails its way through the Gulf Stream, and then goes back on its way at about 12 knots of speed. So you get to see, in this case, you can see sort of how the triangle sort of points, changes, and then actually the ship does this going through the stream, and then turns and heads south again. So the meteorology associated with that, well, they first, this is the way Liv actually broke things down. So looking at a spreadsheet of speed, course, and unfortunately it's not course, it's heading. So that's a bit of a change. So we actually have to kind of figure out what course was at the same time. It's not something that this version of the AIS application actually keeps track of, and I've asked the Navy like 3 times, how come you don't do course? I really want course. Course over ground along with speed over ground. So here you get to see the details of the vessel going through, and one of the challenges is basically determining where does the impact start. So they're actually slowing up in here, which may just be the weather, as opposed to the combination of the weather and the conditions in the Gulf Stream. But you get to see in detail how the vessel is going through the stream, and then to the south at a very, very slow speed, less than 2 knots at this time, and a lot of that at less than 4 knots, or 6 knots through this area.
So is this autopilot?
Are they on an autopilot? They may be. If they're in conditions like this, they're probably self-steering.
So why is it heading west when it wants to go south?
Let's look at the weather. Let's see. Next one, where are we? Yeah, exactly. Okay, we're going to get to that. We're going to get to the answer. Okay, so basically they were going through a frontal system. They were just to the east of a low tracking that was rapidly intensifying. So they had easterly wind, going to southerly wind, going to westerly wind. So the fact that they turned west was to turn into the winds and waves. Assumption, just an assumption. But basically, prefrontal in the warm sector, all the way down to here, and then the wind coming from the west and then northwest. Yep.
And captain's logs don't contain their rationale for doing it.
It may, it depends, but they're kept on the ship.
Yeah. Okay.
Sometimes you're so damn busy, you don't write anything you want when it's
Yeah, actually, well, you were to talk that Jay Amster gave at AMS. Okay, well, I have his logs. there's very little entries during there's about an 18-hour period where he did a summation, but there's no position, location, anything. They're just fighting to survive. Okay, so Fran did some analytics, and this is one that was a little bit of an eye-opener. Okay, there's actually, I only chose one. So what we're looking at is a 60 to 70% reduction in the normal operating speed of the ship. So, for example, for a 15-knot ship, we're looking at speeds between 6 knots and 4.5 knots. Okay, so not a huge, I mean, it's 2/3 of loss of speed, but actually we bend it every 10% up to 90 to 100%. So, here's the stream, and I'm going to show you the locations as to where they are. Okay. Do you think we got a problem with the Gulf Stream? Think we have impacts? So not all of these may be that. For instance, down here, we found this to be really interesting as to why there's such a high concentration out here. Okay. Ships, when they're at sea outside of EEZ, up until January 1st of this year, burn high sulfur fuel at sea. When they come inside the EEZ, they have to transition to low sulfur fuel, which is more expensive and a little bit less economical for the engines, for the diesel engines.
Joe, what's the EEZ?
Oh, 200-mile limit, the economic zone.
Okay.
Yeah. So, this area right here is the Canadian EEZ. So there actually is a crossroads of ship tracks. So here, your arbitrary point in the blank ocean is a very high traffic area because of the fuel considerations to it. So, in essence, because of fuel considerations and cost, they're being forced to sail through the Gulf Stream, even if they're opposing. So, we really had no idea. And some of these out here, out on our EEZ, the U.S. EEZ, may be actually areas where they've slowed down because they're actually changing fuel. But that's just changed because the regulations are now that they have to burn the low sulfur fuel, or they have to do scrubbers, which basically makes the ocean uniform. So it'll be interesting to see what happens.
To slow for a fuel change, you can use 70% of your speed.
It depends on how long it takes. I've heard at times where they basically say they stop. And the other thing, and I don't have any density plots up here, but the way ships leave the coast is to minimize the time they're in the EEZ. So if you're sailing, going to Europe or Mediterranean, coming out of Charleston, in particular out of Charleston or Norfolk, you're going straight east as you can get out of the EEZ as fast as you can because of the fuel considerations. So the first ship I showed you, that's actually what it was doing. So it was going west before it started on its great circle track. And when you look off the west coast, come out of the Strait of Juan de Fuca, come out of San Francisco, you go straight west, minimize your time in the EEZ, and then you start your great circle. So it's all about money.
East of, I can't read what the...
Oh, we're at 55 west.
Yeah, so east of that, do they speed up again and off they go? So they don't show up here? Why is it so...
We weren't capturing them.
We weren't capturing them. Plus, we don't have the location from the Navy. The Navy does not do a Gulf Stream analysis east of about 55 west. Yeah.
They're kind of bifurcates.
Yeah. Yeah. Okay. So I'm going to go through these at once. Okay, so Liv put these together, and one of the challenges was determining when a ship was in the Gulf Stream. Okay, because the 3 analyses a week really doesn't give you the detail as to where, because we were seeing impacts outside of where the Navy Gulf Stream was, and it may have been a couple days old at that point, doing Monday, Wednesday, and Friday schedule. That's what these first 2 are. And the next one was trying to determine with the conditions that we don't have a way. It's in the messaging, but we don't receive it in the messages that we get. Trying to determine the impacts if the ship actually is in ballast or is loaded during the time, especially the in ballast, because that can be wind. For a ship that's really, really light at sea, it can be a wind effect.
And then the other thing was because of time and the amount of manual effort, which we'll if we do something like this again, which I'm hoping we do, we'll have to have this more in an automated way, so they actually were just plotting things. So we only could do about a third of the tracks, and there's another 120 that are sort of beyond that had minor impacts but still had impacts. So this is just sort of a tease or a sampling. Okay, so a bit of the analytics. Fran did these, and this is 50 to 60% reduction in speed based on the wind direction. So the important thing, so there's no ship in here except for it's at the middle. The point in here is for this reduction, we're seeing winds all the way from the northeast all the way around to the southeast. I mean, it does look like there's a moment of a max in here in the northwest, but it's a little bit different. The important thing to us was the old rules of thumb. There were no southerlies in there at all. So this is a 60 to 70%, and you can start to see it starts to favor some sort of westerly component of the wind, even though there is some south-southeast and northeast. But basically, the predominant, at least during this time period, and this is color-coded, anything yellow or higher in here is gale force winds. So, and another thing that kind of alarmed us is you get winds down to 20 knots in here that actually are having impact where ships are slowing down 60 to 70%. So it may not all be wind either. This is the difference between the ship's heading and the wind direction. And what you're seeing, this is a 50 to 60% reduction in speed, 60 to 70, and 70 to 80. As the ship slows relative to its operating speed, you start to see that they're favoring the wind direction to be more forward. Okay, and you'll see another example of that. Okay, this is wave direction this is basically out of wave watch. So we cross-match the vessel positions with wave watch. Like I said, Fran did all of this. And so you're starting 40, 50, and these are in 10 bins, all the way up to 90 to 100%. Color-coded by wave height. So the yellows are 18 feet, all the way up to some of the deep reds in here are 36 feet or greater. And what you're seeing, the higher the reduction in speed, say down in here, 70 to 80%, 80 to 90, or 90 to 100%, basically, they're turning into the seas. So this is basically what's going on, is they're basically being forced to turn into the seas for the stronger seas. Okay, I think we're getting there. This is the speed of GR tops relative to the impacts. So the percent reduction is increasing here up to 100. And so we're seeing basically a max. This is the current velocity versus, and basically this is just a count of based on percentage of reduction in speed. So up to, basically the max is in here somewhere, 1 to 2 knots, yeah, it's just a count. Okay, and the percent reduction. So not a lot of current in the GR tops, basically, and we're seeing, impacts. And these impacts are relatively subtle in here. So that may actually be, if you're getting a relatively low reduction in speed, it may actually be the current in there. But the bad stuff's up here, where they're really reducing things. Okay. This is the speed also. Oh, no, it's the same one. Sorry about that. That's what happens when you don't practice. Okay. This is wave direction. And the message here is the predominant wave direction. And this is dominant wave, I think is what we did?
Primary wave, yeah.
Primary wave. Okay. So has a westerly component. Okay. Everything's from southwest, right in here, with a significant reduction, to westerly to northwest. Okay. So, and that may just be the time of year and the storm track at the time. Okay. So, let's wrap up. So, our point was to document impacts of ships crossing the Gulf Stream. But we don't really know what the conditions are that are actually causing them to slow. Okay, so that's the first thing.
our next thing is that the established rule of thumbs only tell a small portion of the story. I mean, when you look at the percentages, we had a lot of southwesterly generated waves, a lot of southwesterly wind with impacts that were not in the Navy's old rule of thumbs. And those rules, if you think about it, were established for the op areas, the Navy op areas off the coast, where you don't get sort of a long southwesterly for a length of time, per se, where you're dominated by northwesterly. And it's also where the gradient, thermal gradient and the current gradient is so sharp just off the Virginia Capes and down to the southeast. So, in other words, there's a little bit of a bias in their rules of thumb. Okay? The impacts we saw were across the full extent of the Navy's analysis area and as far to the east as southeast of Newfoundland. Waves from the northwest, west, and southwest were predominant, with ships slowing in their transit. Lack of observations is the assessment of ocean model currents on the scale needed to forecast wave current interaction. So both, we could debate this forever. The ocean's still an unknown, relatively unknown compared to, say, terrestrial things. I'm looking at Avishal and Enrique, and you guys certainly know this and advocate for it. But, we have wonderful instruments and all, but not necessarily at the scale that nature actually produces things that impact human activities. Okay. And so we examined impacts, but it was over a limited time period. It is what it is, and there's nothing more than that. And maybe dominated by cyclone passages and the cold air flows of the west of the northwest and even the southwesterly flow. I mean, you just have to kind of go into this with eyes open, realizing that you take away what is there, but realize you didn't do as thorough a study as possible. Okay, so future. We're actually working with NIMS and Ocean Service to basically have in the cloud a depository of global AIS data and an archive. Okay, and really to examine whether it's us or whoever ends up doing it, corresponding weather conditions to impacts. Okay, so in this case, with a focus on the stream, to examine wind wave and swell systems separately versus the current. So we did sort of a cursory thing, but we really need to start to look into, there are things that we don't consider. For instance, when you have southerly and then a northwesterly or westerly wind coming in, you, for a time period, will get a very confused sea. That's what Captain Kavanaugh mentioned. We don't have the tools at this point. We have pieces of it, but we really haven't worked on trying to basically diagnose when we're going to have cross seas, for instance, or confused seas. Okay, and that there's an incentive there for us. The economic impact to calculate lost time and then come back with that. Certainly, our agency would like to see that because when you start to realize you put dollar amounts on this, it's significant. Coupled systems. Enrique, you're going to hear it again. It's not you, I know, but basically, we really need to go to coupled systems to start to at least get a representation of what is going on in an area where we have strong current.
I have good news for you.
You have good news for me. Will it be on my desk in my workstation when I get upstairs?
Yes.
Yeah. Okay. But the challenge is going to be the model currents and the gradients. Are they going to be representative? I mean, we'll get a flavor, but we may not necessarily. I actually think this needs to be observed routinely, and that's a long story, but I was disappointed our European colleagues made a choice between two satellite systems, and they did not choose the one that would have actually started to illuminate the issues with the wind and current and wave interaction. Okay. So this kind of addresses, so what do we do at this point? And I actually think the simplest thing that we can do is make sure that we have Gulf Stream depictions from the Navy on our graphics as best as we can, and sort of leave it to the mariner at this point to determine, because we really can't routinely predict accurately, because we don't observe frequently enough as to what the conditions are going to be, but at least to know the best where the bounds are of the stream. The problem with it is the graphics that we do are in black and white. We also do color versions, and it's the color versions that we would have to add the Gulf Stream bounds to. And there's another side of this, and I actually think that we will see this in my lifetime. We will start to see sort of reversal. The marine industry is very conscious of the fact that they're a big source of carbon. And so they're looking at not just the industry, but the regulators of the industry, the International Maritime Organization, are looking at trying to basically reduce the carbon footprint of shipping. I actually think we're going to start to see sort of reversal of ships basically transiting sort of the old-fashioned way, using the traditional trade routes that were favorable to wind. The other thing they're talking about is possibly regulating the speed of ships. And if you start regulating, some of these container ships can do over 20 knots. Okay, so carbon-wise, that's a bad thing. When it comes to weather avoidance, it's a really good thing, because it's the biggest defense you have is you can move. You know, if you start regulating speed where ships can, say, go 15 knots, now you're putting them in a place where they are going to frequent weather more and perhaps not be able to get out of weather. So I'm going to stop there. Any more questions? Comments?
Again, I have a good news for you. I finished the three-way coupling. It's working. I'm doing sensitivity study on the Gulf of Mexico. And then I noticed that definitely there are wave and loop currents interactions. It enhances downwelling, upwelling along the flank,
yep.
the current's flank. So definitely it can be applied for the Gulf Stream as well. So my tool is ready, and volunteer to run this one in a three-way coupling in the Gulf Stream.
In the Gulf Stream.
Yes.
So in which system? So are you working on UFS, or are you working on the hurricane system?
Hurricane system.
Hurricane system.
But it's
okay.
coupled to HICOM,
yep.
and using WaveWatch 3.
Physics.
So, yeah.
Okay.
Physics is, I forgot. I mean, HICOM and WaveWatch 3, no problem. And you can put the FB3 in it.
Okay.
It's a no problem. So, next
I
test.
know where your cube is.
Yes. The next test is the Hurricane Dorian, and apparently, interacts with the Gulf Stream stuff.
Sure. Oh yeah.
All the atmospheric ocean and waves are interacting each other.
Yes.
So.
Yeah. Yeah. There's actually a time period when Dorian was going north and transitioning, where we got to see where we assume there's a high wind max in the geostation imagery. We saw sort of a milky obscuration of the surface.
Mm-hmm.
We actually think we're seeing spray.
Yeah.
Yeah. We've seen it now 3 times. We saw it in Umberto, and we saw it in the April 2nd storm off of Hatteras that basically was born out of an MCS.
Okay.
And yeah.
Keep that in mind. We are trying to simulate the spray as well. So.
Oh wow.
That's work ongoing.
No, Andre and then Walter.
Yeah, Joe. So your question there on whether the hazard should be based on winds or waves, maybe I'm biased towards the waves, but it seems to me like a ship would be more sensitive to the effects of the wind on the waves and then on the ship rather than the changes in the winds itself.
Yes, I agree. Yeah. I actually, so we're required to warn for wind. It's almost like our requirements have the underlying assumption that we can't predict waves. That may be a little bit naive on my part, but basically, the language in the WMO for Marine Services was changed in the last release, where it basically starts to strengthen the language for warning on waves. And it says should, not shall, but should warn for dangerous seas. They didn't put quotes around it, but they probably should have, because now the question is, what's dangerous seas? So it's kind of in some ways, but it's a start. Yeah. But I agree with, in my own experience, okay, so, it can be blowing like crazy, but if you have a short fetch and you can limit it, you can operate just fine. It's not so wind dependent. But, if you're in an exposed area where the fetch is long and it's blowing, you got to, I remember going through a funnel passage one time, and it was wicked. 70 knots out of the south and went to about 45 out of the northwest. Ship did not know which way to go. There was no direction to point the ship without just slamming every once in a while or taking seas on deck. It was about 25 minutes, but it was a kind of a thing. Is all it takes is one incident where bad things happen.
Yeah, and if you're focusing just on the wind, the directly wind-generated wind seed, you're missing maybe half the story because there could be swells completely unrelated to that.
Yeah, and that's the point of the Gulf tanker that I showed at the beginning. That this is a distant storm that is impacting locally, and actually did quite a bit of damage to the ship. Walter.
It's another great seminar, Joe. They're always exciting, and I always learn a lot of stuff about it. You said,
Thanks.
I think, that you're talking about the scatterometer observations of wind and saying that they didn't get higher than some number. Of course, the actual winds go very much higher. What about the altimeters, and is there any difference between Altica and Ka band and the others, the Ke band, as far as how high, up to what point are they accurately giving you high winds? Do they also saturate at some point or become useless?
So, okay, I'm gonna answer this in sort of a not so good way. Is because of the coverage of the scatterometers, we pretty much depend on the scatterometers. We do have available the winds from them, but we're not banking a lot on the winds from the altimeters, which is sort of a.
And we can't see all of them. Just it's a hard-coded problem inside of NAWIPS that we cannot get NCO to fix for us. So there are several of those satellites we cannot see the winds for in our workstations.
Yeah.
Okay.
Yeah.
Maybe, I don't know, that could change, but in general, I guess this thing sort of gets asymptotic, so that once the winds become very high, they can become essentially infinite without changing the radar backscatter very much.
Yeah.
I was just wondering if there was a margin between what scatterometers could do, if altimeters could go a little bit farther or not, and if it makes a difference to Ka and Ku. I was just curious. I don't know.
Okay, I don't know the answer to that. I know that our European colleagues in the follow-on to the ASCATs, the last ASCATs up there, ASCAT-C, SCA, which is a very hard thing for me to say with my Boston accent, but it's SCA, basically is the acronym for the next series of scatterometers, the follow-on. And what they've done with that is they've looked at the polarity and the sensitivity. So the C-band scatterometers will be able to detect higher winds than the saturation point that we have now. The saturation will move up to about 120 knots or so. Now, that means nature has to produce 120 knots on the scale of the footprint of the scatterometer. Different problem. So in other words, if the goal is for tropical cyclones, you're not going to see that. But you will see in the mid-latitude cyclones where the wind footprint is much larger, so we think, then we should be able to actually start to see, if there are higher winds, we should be able to actually see them.
And one trivial little thing, I think you said you get in this data the ship's heading.
Yes.
And the ship's speed through the water. Or
speed over ground and heading.
Well, over the ground or through the water? I mean, is it Doppler speed log? Is it screw RPM? Is it, what's it?
It'll be GPS calculated.
Okay. So that's a real speed made good.
Yes.
But do you get from that also the real heading made good to compare with the ship's bow direction? Which one do you have? Do you have one or both? Or the other?
We just have the heading. We don't have the heading made good.
But that could be easily calculated in the time series of lab one.
And that's kind of what we tried to do.
Yeah,
Go ahead, Jason.
Yeah, that's what we've done. We've just calculated it from the next point.
Yeah, just use displacement. Yeah.
Because I would think maybe the difference in those two things, in other words, what the ship, where the ship has headed itself and what it's actually making over the ground, the difference in those two is probably a good proxy for your loss or your impact.
And that was one of the things I wanted to look at, but I had not gotten it. I didn't have it programmed in the Python that I was doing, because I was doing a machine learning linear coefficients, just to sort of pick out which parameters, throw a ton of parameters at it, which things are actually perhaps predicting the speed. And I wanted to put that one in, and I didn't get that one in. But the wind waves were way up there.
And like I said, we've actually asked that the Navy basically set up the parameters, and the Navy, with their concern. And so we went back to Navy, Fleet Forces. Actually, it's SPAWAR out in San Diego. And we asked them, is it possible? And they said, wow, that's a really good idea. They haven't done it yet. Is basically to put that, because that is in the AIS message, but they just haven't, it's not their interest. Anyway, but it is a different era. I mean, we can look and see where ships are now globally. We watched, after the fact, we recreated the track of the Bourbon Road that was lost in Lorenzo. And frankly, it's horrifying. That vessel practiced no weather avoidance whatsoever. It drove right into a hurricane. In this age, with all the sophistication of information that we have. In some ways, I think it's actually worse than El Faro. They basically had about 4 hours where they continued on the same course. Their heading was different because at that point they were in the storm and basically being driven into the storm. And they were in a northeasterly flow, and they were being pushed along at 7.5 knots, and ended up right in front of Lorenzo. As you know, 11 were lost. 3 actually were rescued out of in a raft. And Noah, this was when they were going to fly in Lorenzo, based out of Barbados, in the P3. 43, I think, was actually tasked with doing search and rescue, and they were looking in tropical storm conditions. It was blowing 35 to 40 knots in showers, and they were out there looking, and they actually did find something that they were able to find the next morning, and actually found the individuals. Thanks, I really appreciate it, the opportunity to talk. So.